R script. That's what we'll kind of be working out of a little bit here. Once you get done with that, the second thing you're going to need is the data itself. You can get that from kaggle.com/c/Titanic. Okie doke. So yeah, we can pull up that R script that I sent out. Did everyone get the chance to download that and open it in R? Better question, did anyone not? Does anyone need more time and or help?
Can we increase the zoom on this?
I don't know. All right. First thing we got to do is load the data in. So I have my directory set because I have it in downloads, but you'll have to set your directory to wherever you saved it. It'll probably be different for Windows rather than Mac. Alternatively, you can import data set here on the right. From text. You can go to wherever you downloaded it. For me, it was in downloads. Or actually, I think I just saw it. Add it in. I don't remember. Wherever you saved yours. And then you can just go ahead and double click it. Should be able to save it as df.train. You'll want to keep it the same name just so you don't have to change things later on. Make sure you import the train CSV as df.train and the test CSV as df.test. At any point, if there are any questions, feel free to just raise your hand, stop for a second, we can help you out.
Shout them out.
So if you have it in the script up here, you can hover over it and click Run up here, or you can hit Command Enter, Control Enter if you have Windows. Either of those runs the line of code in your script. So here I'll go run the next two. So right here, I've imported df.train and df.test. After that, you're going to want to import all your libraries. You might not have all of them installed. You probably won't, depending on if you've used them or not. So you'll have to install the packages. But for me, I already have them, so I'll go and run all these. But if you don't, then you'll want to go to this install packages line. Let's say you get an error on deployer. Then you'll go install packages, deployer, run that, and then install it. It'll take a sec, and then just do it for all the ones you don't have. Give you a sec to get all that. Sorry, setting it up just takes a minute or two. All right. So I'll hope that you're kind of here at this point. So let's start right here. So we're going to go over a basic overview of the data, kind of look into what we have here. We know that it's a data set containing information about every passenger of the Titanic. So that's what we know so far. So in order to take a look, we're going to use the view command. So go ahead and write view with a capital V. If it's lowercase, it won't work. View df.train, and then go ahead and run that. And here, that'll pull up the data frame. And we can see that there are 891 observations in this data set. It's a table that includes all their passenger IDs, whether or not they survived. This is coded as a dummy variable, which basically means if it's equal to 1, it means they survived. If it's equal to 0, they didn't. We have a variable called P class that indicates the class of the cabin that they're in, i.e. first class, second class, third class. It kind of gives you an idea of the passenger's socioeconomic status. We have all their names. we have their sex, male or female. We have their age. You might notice that some of these ages are NA, so we have some nulls. We'll deal with that later. The sibling, the SIBSP is sibling spouse, indicates how many siblings and or spouses they have. Some came alone, some came with one. The next one is PARCH, that indicates how many parents and or children they have. We have a ticket variable, which is literally just what their ticket comes out as. We have the fare, which is how much they paid for their ticket. We have cabin, which is what cabin they're in. Lots of nulls here as well. And we have embarked, which tells us the city in which they embarked. There's 3 different cities. Don't remember which one's which, to be honest. Watch the movie. Okay. So next thing we're going to do is we're going to use the mean command. We're going to use mean df.train. That's the data frame that we're getting information from. $, survived. We're pulling up the survived variable. Survived variable from the df.train data frame. We'll run that, and we'll see that the mean is 38%, 0.38. And what that's doing is that's finding the mean of all of the survives, which are coded as 1s and 0s. And what this interprets as is the percentage of people who survived the sinking of the Titanic. So 38% of people made it, which means roughly 72% didn't. That gives us kind of a basic idea of what we're here to look at. And then we might want to look at further insights. Right now we're looking at a bunch of summary statistics, so we're not doing any real analysis. We're kind of exploring the data, seeing if we can find general trends. So we might be interested, you can see here that I kind of put a little note. Does cabin class have an effect on likelihood to survive? If you watch the movie, which I haven't in a very long time, but it's pretty apparent that socioeconomic status plays a big role in who survived and who didn't. Those in the lower classes just did not do quite as well. So I won't go too into detail, but this line of code is basically going to pull up, let's go ahead and run this right here, a nice little table that splits up each of the classes, first class, third class, first class, second class, third class, the amount of observations, and the percentage of those which survived. So you can see that in the first class, 63% survived. In the second class, 47% survived. In the third class, 24% survived. That gives us a pretty good idea that, yeah, they're probably right. The lower classes do not quite have as high a chance to survive. But we might be interested in looking even further at doing what we might call an interaction, which is basically taking 2 variables, multiplying them by each other to get specific combinations. This next code splits up by class as well as by gender. So if we run this next command, we'll see that there are now 6 rows, 2 for each class, split up by male and female. So out of the 94 first class females, 97% made it. So they had a really good shot of surviving. Third class males, only 13% made it out of 347. That's yeah, not too great, but you know, we're just looking at basic data exploration to see what we can find from just preliminary insights. So that kind of gives us a good idea of things that we can be looking at to include in our model. These are just a couple of things. We could spend weeks or months on this one project, which we're not going to do. We're going to just spend an evening on it, an hour or two. So I encourage you on your own time to, further explore other relationships that you can include in your model, because that's kind of all about what data science is all about, is discovering relationships. So now we're going to get into our next section. That age group, we might be interested in observing age groups in bins. What I mean by bin is grouping the age groups in terms of like a child, maybe a teenager, an adult, the elderly. In this case, what we did was we ran anyone under the age of 5, we called a young child. Anyone between the ages of 5 and 14 are a child. And anyone above the age of 14 we called an adult. I won't get too into detail on the if-else command, but if you have any questions about that or want to learn about it, feel free to come talk to us after. So let's go ahead and run that. And then we'll want to make sure that we set the embarked variable as a factor. I won't explain that too much right now. Just for right now, trust me and run that one, and then we'll head into setting up the logistic regression. So before we actually get into setting up the logistic regression, I want to give a little explanation of what logistic regression is. Just out of curiosity in the room, does anybody somewhat kind of have an idea of what logistic regression is, or maybe you know what it is, you've worked with it? Anyone in the room? Perfect. Well, logistic regression is a form of binary classification. If you weren't here at our last meeting, we went over different types of algorithms in machine learning, which at its start can be broken into supervised and unsupervised machine learning. We're not going to worry about unsupervised. We're just going to talk about supervised machine learning, which can be further broken down into 2 types of algorithms: regression algorithms and classification. Classification is interested in finding relationships that can group similar individuals together. So in this case, we're interested in predicting whether or not somebody survived or not. A regression algorithm is it has a continuous variable as an output. So you might be interested in finding out, let's say we have data on grades and your wage on your first job out of college. You might be interested in finding out, if I increase my GPA by 0.1, how much will my wage increase? Will it increase by $500 per 0.1? Something like that. That gives you an example of a continuous variable as an output, which is a regression algorithm. Classification is one or the other. Sometimes you can have multiple groups. Well, by multiple, I mean more than 2. But right now, we're just going to talk about binary classification, which is a classification which only has 2 outputs. 1, 0, male, female, yes, no. These are all different types of outputs. And the way it works is logistic regression, in terms of its interpretability, is very similar to linear regression. If you've worked with linear regression, you'll be able to understand the output of logistic regression. Have you guys ran some sort of ordinary least squares OLS regression and seen an output? You have your coefficients, your p-values, and you feel somewhat confident in interpreting those. Luckily, if not, that's okay. We'll get into what that means later on. But if you have seen that before, it's very similar. So logistic regression works by essentially calculating probabilities and then kind of converting it into odds. So the difference between probability and odds is, you know, I have a 50% chance of going to class tomorrow, or my odds are 2 to 1, or not 2 to 1, 1 to 1. Whoa. Oh, sorry. Do you still need that? Oh, yikes. Sorry, I needed the whiteboard a little bit. So the issue with probabilities is that it's a percentage. It's between 0 and 1, so your range is limited. With linear regression, your range is not limited. It can be, your output can go up to positive infinity. It can go down to negative infinity. With linear regression, you don't have that limitation. With probabilities, you do. So if you convert your probability to your odds, that increases your range from 0 to positive infinity. If you guys have ever seen like Vegas betting odds, they use odds. What are the chances the Seahawks win the Super Bowl next year? Maybe it's 12 to 1. Maybe it's 20 to 1. Maybe it's 1 to 1. Maybe it's 1,000,000 to 1. The positive end is unbounded, but the bottom end is 0. It cannot go, odds cannot go below 0. I won't go into the math, but log odds, by taking the natural log of your odds, bounds the bottom to negative infinity. Your log odds can go down to negative infinity and go down up to positive infinity. So that takes away the problem of boundedness. So with that being said, logistic regression can be interpreted very similarly to linear regression, because now you've taken away this issue of the bounds. Does that make sense? Okay. So what this ended up...
Can you explain a little bit more of the bounds? Like, I'm kind of confused as well what you mean by, like, what's it mean? Do you, like, give a real example?
Well, when I say bounds, I'm talking about the range of outputs. So the example...
Like, could you, like...
well, I don't know if there's like a real world example per se, but a probability is like 0 to 1.
Okay.
The range, the bounds, you could say, are 0 and 1.
Okay.
Cannot go above 1, cannot go below 0. Okay. You're stuck with that. And in terms of... All right, so the first thing that we're just going to do real quick, just run this set seed 1. The reason we're doing that is because we're going to find some random sampling. And this will set all of our random samples to be the same. If you hit set seed 2, it'll be a different random sample. Set 3 is a different random sample. But if we all do set 1, we'll have the same sample, which means we'll have the same outputs. So we're going to split our data into a training set and a test set. I'll explain to you why. Well, actually, I have a video pulled up for you, which I thought explained it very concisely. That already pulled up. Yeah. You guys have any experience with cross-validation and or resampling? So this is basically kind of explaining why we need to validate our data.
How many groups do you want? We talked about this briefly.
Okay, we're not going to get too into detail on the types of validation. In fact, we are not actually even going to use cross-validation in this one. However, if you end up doing this project by yourself, to maybe challenge yourself a little bit more, I encourage you to. We're going to do what he mentioned in the beginning, which was splitting your full data into training and test. So, like he said, you split a certain percentage of your data into your training data. In our case, it's 0.8 right here. So we're going to take 80% of our data and assign that to be the training data, and the rest is going to be your test data. So the idea is that we will create a model that learns relationship based on 80% of the data and then test it on the other 20%. Does that make sense? Anyone have questions about that?
So if it's the same thing, do you know that you're correct? Or?
Well, in our case, we're doing classification, so we can just directly compare our prediction. So we're going to predict on the other 20%. We're going to predict whether or not they survive, and then compare it to compare it to the actual results. So we're going to take our predicted results versus actual of the 20%. Okay. So go ahead, set your seed, run that line, set up your training set, and then we'll go into defining the formula for logistic regression. So, yeah, go for it.
So we downloaded like a